Welcome friends. We are discussing network theory. We are presently at module 8, which is actually introduction to Laplace transform. In the last session we have briefly discussed the definition of Laplace transform, few important properties, and what is the Laplace transform of some standard input signals. In this session, we shall solve some problems regarding the Laplace transform. So let us first solve the problem which is based on initial value theorem and final value theorem. So initial value theorem is actually limit t tends to 0 ft, which is equal to limit s tends to infinity s into fs. What is fs? Fs is the Laplace transform of ft. Fs is the Laplace transform of ft. And we have final value theorem. Final value theorem is limit t tends to infinity ft, which is equal to limit s tends to 0 s into fs. Again, fs becomes the Laplace transform of ft. So using these fundamental theorems, we will evaluate initial value and final value of a function. So according to initial value theorem, if this is the function, fs is equal to s plus 10 divided by s square plus 3s by 10. So its initial value, according to the initial value theorem, if we substitute limit s tends to infinity s into fs. So here s into fs, that means in the numerator we have s square plus 10s, and in the denominator we have s square plus 3s plus 2. So we have limit s tends to infinity. If you take a square common from both numerator and denominator, it will be 1 plus 10 by s, and from the denominator we have a square common, 1 plus 3 by s plus 2 by s square. So now as s tends to infinity, this 10 by s goes out to 0, this 3 by s is also goes out 0, and 2 by s square is also goes out 0. So it will be this s square and s square cancels out, so it will be 1 by 1, so it will be 1. So initial value of this function is 1. Now what is about the final value theorem, or what will be the final value? So you limit, put the formula limit s tends to 0 s into fs. So limit s tends to 0. Now in the numerator we have s square plus 10s, in the denominator we have s square plus 3s plus 2. So if you substitute s equal to 0, so in the numerator we have 0, in the denominator we have 2, so it will be 0 by 2 is equal to 0. So for a function s plus 10 by s square plus 3s plus 2, so if we plot if we plot this function in its time domain t, x-axis t and y-axis ft, so what does it mean? From the initial value theorem we are getting the function value is 1. So what is 1? So function value is 1 at t is equal to 0. So that is the initial value theorem, or initial value of the function, and it has value of 0 at t is equal to infinity, or final value. Okay, so it should be something like the trajectory should be, it's roughly like this. That means trajectory is not important, but it starts with the initial value of 1 and ends with a final value of 0. That is the meaning. Let us solve another problem on this. Let us say we have this time fs is equal to s square plus 5s plus 7 divided by s square plus 3s plus 2. So now if you evaluate the initial value theorem, so your formula is limit s tends to infinity s into fs, so the numerator becomes s cube plus 5s square plus 7s, and in the denominator we have s square plus 3s plus 2. So from there, if we take from the numerator, if we take s cube common, then it will be 1 by 5 by s plus 7 by s square. Now in the denominator, if you take s square common, so it will be 1 plus 3 by s plus 2 by s square. Now with s tends to infinity, this 5 by s, 7 by s square, 3 by s and 2 by s square all will be 0. So it is only remaining s cube by s, so which is equal to limit s tends to infinity is only s, so which means the initial value of the function is infinity. And according to the final value theorem, if you put limit s tends to 0, s cube plus 5s square plus 7s divided by s square plus 3s plus 2, so it will be simply numerator 0, denominator 2, so it will be 0. So that means if you plot this function in the time domain, if you plot this function in the time domain t versus ft, so it starts with the initial value of infinity, that is a huge value, large value, and it ends with a final value of 0. And trajectory may be something like this or any kind of the trajectory, but it means it initially at t is equal to 0, it starts with the value of infinity, and at t is equal to infinity it ends at 0 value. So this is the significance of initial value theorem and final value theorem. These two theorems, initial value theorems and final value theorems, are useful to evaluate the initial value of the function and final value of the function. Very straightforward. You just should know the basic mathematics of 11-12. That's it. You can solve this problem. Now moving on. Now suppose any function ft, you apply Laplace transform on that function, you will have fs. Now suppose if you have fs, then from that fs you should know, or you should get back, or if you want the time domain function, then what should you do? Suppose you have a time domain function. In order to have the Laplace domain on frequency domain function, you apply Laplace transform on this time domain function. On the other hand, now if you consider you have the frequency domain function fs, now from that function if you want to have your time domain function, then what should be the process? Now you should revert that process, you should inverse that process, which is called inverse Laplace transformation. Inverse Laplace transformation. So we will solve some problems on inverse Laplace transformation, and it is extremely useful technique to solve network problems, that is inverse Laplace transformation. Now what to solve? Now, it's very easy. Suppose you have sine omega t, its Laplace transform is omega square divided by a square plus omega square. So suppose if you have a function fs is equal to, let us say, 4 a square plus 4. Suppose you got this function. So basically it can be written as 2 square divided by a square plus 2 square. So from there, if you remember this rule, transformation rule, that is Laplace transform of sine omega t. So from there you can directly write, if fs is this, then ft must be sine 2t. Sine 2t, where omega here is equal to 2. Here omega is equal to 2. Okay. So in this way, if you know the direct relation, that is time domain to frequency domain, so you can just reverse the process and to get the function in the time domain. It's a very simple process. Now with the help with that technique in our hand, we shall solve some inverse Laplace transformation. Okay. Suppose for the first problem, if you see fs is equal to s plus 2 divided by a square plus 4s plus 7. Now how to get the inverse Laplace transform from this expression? Now you should know the technique. Now first of all, you see in the numerator we have s plus 2. That means if you look carefully, s plus 2 means what? It is shifting in the time, it is shifting in the frequency domain, s plus 2. So you should utilize this property, the shifting property. That means you see this shifting in the frequency domain, that means what? Multiplication in the time domain. So you should utilize this property. You should try to utilize this property. That is, frequency domain shifting means time domain multiplication. So since we are having a argument which is s plus 2 in the numerator, so we try to arrange our denominator in somewhat in this form, s plus 2. So we try to arrange. Okay, so let us say we write s square plus 2 into s plus 2, 2 into s into 2 s into 2 plus 2 square. So now you can think that, or you can understand that this is nothing but s plus 2 whole square. This is nothing but s plus 2 whole square. What is that? S square plus 4s plus 4. Now in the denominator, what is there? It is 7. So what is to be written additional? It is plus 3. Right? It is plus 3. So we can simplify even, then it is equal to s plus 2 divided by s plus 2 whole square plus, now you can write 3 as root 3 whole square. 3 whole square. So this is your fs. From there you can, or you should try to identify the well-known form. That means in which transformation you observe this form. Okay. So if you look carefully, what is cos omega t? What is cos omega t? That is what is the Laplace transform of the cos omega t? So it will be s divided by s square plus omega square, right? Now if you analyze, or if you if you compare these two, you see in the numerator we have a s, here also we have s, in the denominator we have s square, we have also s square. Now for both of the case is shifted by 2. Okay, now in the denominator we have root 3 whole square, so here it is omega square, that means this root 3 must be omega. So root 3 must be omega, so it will be ft. So if you convert its Laplace transformation, ft, it must be cos root 3 t, cos root 3 t. Okay, now since it is shifted by 2 unit in the frequency domain, then it must be multiplied in the time domain, e to the power minus 2t into cos root 3t. So it will be, it is the inverse Laplace transform of this function. So let us recap one more time. We have compared this form s plus 2 divided by s plus 2 whole square plus root 3 whole square with this standard cosine transformation. So if you compare these two, we can understand that omega is equal to root 3. Omega is equal to root 3. So we can directly write, so if this expression fs, if fs is nothing but s by s square plus root 3 whole square, then we can directly write ft from there. Ft we can directly write cosine of root 3t. But instead of having this form, this s is shifted by 2 units. S is shifted by 2 units. Okay. So with the property we have seen, that is property number 6, what we have discussed in the last session, that is any shifting in the frequency domain, that inevitably means that is we must multiply with a time domain factor, which is e to the power minus at. So with now this problem, it is shifted by 2 units, that means we have s plus 2, we have s plus 2 here, so it must be multiplied in the time domain by a factor of e to the power minus 2t. That is why this term came in this problem. So since it is a shifting by a factor of plus 2 in the frequency domain, then it must accompany by a multiplication in the time domain, which is e to the power minus 2t cosine root 3t. So if we have fs is this, then its inverse Laplace transform is nothing but e to the power minus 2t cosine root 3t. That is the inverse Laplace transform of the first function. Now if you look the second problem, so you can solve the second problem in a same way. So in the denominator we write in the same manner s square plus 4s plus 4 plus 1. So that is s plus 2 whole square plus 1. Okay, so we have this function fs, we have 5 divided by s square plus 4s plus 5, so which is equal to 5 by s square plus 4s plus 4 plus 1. So with that we can write fs is equal to 5 by s plus 2 whole square plus 1 whole square. Clearly we can write. Now I am writing the, if you have the sine omega t, if you have ft is equal to sine omega t, then your fs will be omega square divided by s square plus omega square. Okay, so these two forms are very close, but one difference is that here it is a time shifting. So if fs is this, fs is 5 by s plus 2 whole square plus 1 whole square. So you can write 5 into 1 square, it will remain as same. So actually it is actually if you invert it, so from here if you invert it, then due to this shifting in the time frequency domain, you should have a factor of e to the power minus 2t just discussed right now. Okay, it should be e to the power minus 2t into, now it is a sine, so here 1 is omega, so it will be just sine omega t or sine t. Okay, and what is about this 5? 5 is constant, so it will keep outside. So the inverse Laplace transform of the second function is nothing but 5 e to the power minus t into sine t. It should be sine, not cosine. So there is a mistake in the printing, it should be sine t. If it is a cosine, then there must be some s in the numerator. So we have the third problem with us. That is six by s square plus 5s plus 6. We have fs s square, in the denominator we have s square plus 5s plus 6, and in the numerator we have that is, let me check, it will be 6. So now this problem can be solved in two different ways. I will show you both. Okay, so now it is 6. Now if you factorize the denominator, it will be s plus 3 into s plus 2. S plus 3 into s plus 2, which is nothing but s square plus 5s plus 6. So now if you write it like this, s plus 2 minus 1 by s plus 3, then it can be written in this fashion. So 1 by s plus 3 into s plus 2, which can be written as 1 by s plus 2 minus 1 by s plus 3. So now if you consider this expression, so you see if fs is just 1 by s, so from there we have ft is equal to 1. That means it is the inverse Laplace of a unit step. It is the inverse Laplace transform of unity step. but we have added dimension here, that is, it is a shifted in the frequency domain by 2, so it must be multiplied by a factor of e to the power minus 2t in the time domain. So if you directly write the inverse Laplace transform from Fs, it should be 6 should be kept outside. So 1 by s plus 2, it should be e to the power minus 2t into 1 minus, now 1 by s plus 3, it should be e to the power minus 3t into 1. Now again explaining why this e to the power minus 2t, e to the power minus 2t because of this shifting in the frequency domain. Why this e to the power minus 3t? It is due to the shifting in the frequency domain by a factor of 3. Now why this 1? Because it is a unit step, 1 by s. Because it is a unit step, 1 by s, we are obtaining inverse Laplace transform of it. So that is why we are getting 1 in the time domain. So if it is okay, then we got the final answer, ft is equal to 6 into e to the power minus 2t minus e to the power minus 3t. That is the inverse Laplace transform of this function. Now it can be solved in another way, which is called partial fraction expansion, which is called partial fraction expansion. So if Fs is this, Fs is 6 by s square plus 5s plus 6 is equal to 6 by s plus 3 s plus 2. So you write this is as a divided by s plus 3 plus b divided by s plus 2. So in this way we can write, so a and b are constants, a and b are constants. So what is the value of a? A should be is equal to s plus 3 into Fs at s is equal to minus 3. S is equal to minus 3. And what is the value of b? B is equal to s plus 2 into Fs at s is equal to minus 2. Okay. So when you evaluate a, you should multiply this s plus 3. That means what is there with a, it should be multiplied with the original function Fs, and you then substitute s is equal to minus 3. So let us solve. So what is Fs here? 6 by s plus 3 into s plus 2 into s plus 3. Okay, so it should be multiplied with the s plus 3. So it is s plus 3 cancels out. So it will be 6 by s plus 2. So if you substitute minus 3 here, so it will be minus 3 plus 2. So it will be minus 6. A is equal to minus 6. Similarly, if you evaluate b, b will be 6 into s plus 2 divided by s plus 3 into s plus 2. So it will be 6 by s plus 3. So if you substitute s is equal to minus 3, so it will be evaluated 6. So your Fs will be minus 6 by s plus 3 plus 6 by s plus 2. So if you take 6 common, so 1 by s plus 2, its inverse Laplace will be e to the power minus 2t. and 1 by s plus 3 inverse Laplace, it will be e to the power minus 3t. So in the both the way you can solve the problem. Basically this partial fraction expansion, this method will be tremendously helpful if you get a larger function like cube or s to the power 4. So in this type of function, this partial fraction method is very useful. So we have the last function. In this presentation, we have s minus 1 fs is equal to s minus 1 divided by s into s plus 1 whole square. So if you solve this method by partial fraction expansion, then it should be written a by s plus b1 by s plus 1 plus b2 by s plus 1 whole square. So this s plus 1 whole square will have two products. One is s plus 1 itself and another one is s plus 1 whole square. So this function can be split into in this form, b1 by s plus 1, b2 by s plus 1 whole square. Now if you solve a is very straightforward. What is a? A is s into fs, s into fs at s equal to 0. So what is s into fs? A is equal to what? S into fs at s equal to 0. So what is fs? Fs is this. So if you multiply this s with fs, so it will be simply s minus 1 divided by s plus 1 whole square. So if you substitute s is equal to 0 here, so a will be simply minus 1. Now similarly, if you solve for b2, it will be same. So s plus 1 whole square fs at s equal to minus 1. So it will be s minus 1 by s, right? So if you substitute s equal to minus 1 here, so it will be 2. Now b1 is something different. So what is b1? You have to take the first order derivative. Okay. So you need to take first order derivative. So what is b1? It will be dds into s plus 1 whole square fs at s equal to minus 1. So just you need to calculate what is s plus 1 whole square into fs. So it is s minus 1 by s. So you need to take the derivative of this function. So which is s square, then s, and then we have minus of s minus 1. So if you substitute s is equal to minus 1 here, so it will be just 1. So with that, if we write fs is equal to a by s, initially we have written. So what is a? A is minus 1. So we write minus 1 by s. Then we have written b1 by s plus 1. What is b1? b1 is 1. So we write plus 1 s plus 1. And then we have b2 we have evaluated as 2. So it will be 2 by s plus 1 square. So now if we apply the inverse Laplace. So what is the 1 by s inverse Laplace? It is simply 1. Because if it is a unity step, Laplace transform of a unity step is 1 by s. So from 1 by s, if we do the reverse, so it will be simply 1. So we write 1 with of course a minus sign. Now for the same reason 1 by s plus 1 it will be e to the power minus t, because it is a shifted by some amount plus 1 unit in the frequency domain, so it must be multiplied in the time domain by that factor e to the power minus t into 1. Of course 1 because it is a unit step, it is 1 by s. Okay. Now finally it is 2 by s plus 1 whole square. Now what is meaning by that? Now if it is a 2 by s square, then it should be 2t, right? It should be 2t, because if you have t, that is the ramp function, its Laplace transform is 1 by s square. So if you have 1 by s square, then its inverse Laplace transform will be t. So if in this function you have 2 by s square, so it is having 2t. Additionally, you have a shifting in the frequency domain by a 1 unit. So you should multiply it with that factor e to the power minus 1t. So the inverse Laplace of this function is 2 into e to the power minus t into t. So that is the inverse Laplace transform of the this function. So I am repeating, 1 by s, no issue with that, it is simply 1. It is the inverse Laplace transform of 1 by s. 1 by s plus 1, we should have this term because it is shifting in the frequency domain. So one component must be accompanied in the time domain which is multiplying, that is e to the power minus t. Now in this case 2 by s square, if it is a 2 by s square, then it will be simply 2t. Okay, if it is a 2 by s square in the frequency domain, its inverse Laplace transform becomes 2t. Now from that property we can understand that here 1 is shifted, that s is shifted by 1 unit. So if we apply inverse Laplace transform, then it must reflect into the multiplication in the time domain. So that is multiplied by this factor e to the power minus t into t. So the total relation, or the total function is the inverse Laplace transform of that function given in this problem is nothing but minus 1 plus e to the power minus t plus 2t e to the power minus t. So this should be the answer. So this inverse Laplace transform technique is nothing new. This inverse Laplace transform technique is nothing new. It is just opposite of Laplace transform. If we have a function value 1, or suppose we have a 10 volt source, 10 volt or 12 volt battery. So if we apply the Laplace transform on the 12 volt source, it becomes 12 by s. Simple. If it becomes 12 by s. If you think backward, or if you think reversely, so in any problem if you encounter 12 by s, then it should be 12 in the time domain. So just it's a reverse process. Okay, it's nothing new. It's already given in the Laplace transform. The information what you are searching for, it is already given in the Laplace transform. Okay, so with this I am ending this session here. From the next session we shall see some more problems on the variety types of signals. Okay, if we have certain signals, okay, then what will be the Laplace transform of those signals? Okay, so let us end here, and we shall continue this topic from this next session. Thank you.